Welcome to video number 3. Today I'm going to evaluate this definite integral using some contour integration. So let me show you the contours I'm going to use and then explain why it makes sense to use them. So here's the z-plane. I'll consider this x variable as if it were actually z, a complex variable. And I'm going to integrate along 3 different contours. This first one I'll call alpha. Goes out from 0, from the origin, to this point on the positive real axis, r. Later on, I'll take the limit as r goes to infinity, and that's going to end up providing me with this integral here. But then I want to also take this contour down here, which will have a length of r, and then complete the triangle with this contour, which of course has length r times the square root of 2. And it turns out that the most convenient orientation for these contours is like this. I'll evaluate sort of forward along this one and downward along this one. And instead of considering this direction, this orientation of this last contour, and arguing that the contour integral in a loop must equal 0, since there are no singularities of any kind in this region, in fact this is an analytic function, I'm actually going to orient it this way. And I will consider this integral as being 2 ways to write this integral from 0 down to this point here, which is r minus IR. And a perfectly good way to restate the Cauchy's theorem is as saying that the contour integral won't depend on which path I take from 0 to r minus IR. So rather than saying the integral around a loop is 0, I'm saying the integral along 2 different paths from the same place to the same place are going to be equal. So I'm going to argue that the contribution from alpha plus the contribution from beta is going to equal the contribution from gamma. I'll explain why I want to use these particular contours, and what's going to actually happen is that the integral along alpha will give me this integral I'm interested in once I take the limit as r goes to infinity. So here I really will get the integral from 0 to infinity of e to the minus ix squared dx. The integral along this, I mislabeled these. This is alpha. This is beta, and this is gamma. So the integral along the beta contour is actually going to go to 0 in the limit as r goes to infinity. I suppose I want this plus to be black. So I'll argue why that's the case, but it's not too hard to believe. As the real part of z gets big, beta is getting pushed out further and further, and that's going to make the frequency of oscillation higher and higher, so we should expect smaller and smaller contributions. In fact, the integral of something oscillatory over a large region compared to the wavelength should be inversely proportional to the frequency. So we can expect, the frequency will grow like r as we move things out. So we should expect something like 1 over r from the integral near this point. So that 1 over r contribution will disappear. We'll actually see that around this point we'll also get a very small contribution to the integral, and it'll be even smaller. It'll be exponentially damped, not just of order 1 over r. We expect most of the integral to happen, or most of the contribution to the integral to happen around here, and I'll explain why in just a second. But we'll actually see that this green integral along gamma will be a small constant prefactor. This should now be in green. I mixed these up. A constant prefactor, e to the minus I pi over 4, times this known Gaussian integral from 0 to infinity of e to the minus r squared dr. Okay, so that's a known Gaussian integral that's not too hard to do. And by showing that this blue integral will disappear in the limit, we'll be able to equate the thing we were trying to evaluate to this thing that we know how to evaluate. Okay, so why is the contribution to the integral small at these endpoints, and how is that going to allow us to see that the integral along b is 0, or beta is 0. We'll see in a second. First, let's just double check that the integral along alpha is going to give us what we want, because let's see what it's going to be. Integral along alpha e to the minus iz squared dz. Okay, so let's first see what's going on with the change of variables we need to make. We'll parameterize this contour simply by the real part of z. So on alpha, z equals x, and x goes from 0 to big R. So we should expect that this would be equal to the integral from 0 to big R of, well, I have e to the minus I z squared, well, z equals x, and then dx and dz will be equal to each other. We don't need to include any extra factors. So this really is the integral we want. In the limit as r goes to infinity, it's the thing we were trying to calculate. So that confirms what's going on with the red piece here. But now we want to see maybe the green piece, and then I'll save this for last. But already we should be wondering why this angle is minus pi over 4. And we can readily answer that. We want a Gaussian integral on the right-hand side here, because we know how to evaluate one, which means we need to choose the phase of z, well, and it's written x here, but we need to choose the phase of our variable in such a way that the phase contribution from squaring the input variable will, once multiplied by this, give me a negative real exponent. So the beauty of this angle, pi over 4, minus pi over 4 rather, is that when I double this angle, which is what's going to happen when I square my input variable, I get minus I. Or rather, I get minus pi over 2, and when I exponentiate that, I get minus I. That's going to multiply with this minus I to get minus 1. And that is going to be the prefactor minus 1 here in front of this r squared. So let's see how that plays out. So I want to know the integral along beta of e to the minus I z squared dz. And what do I know? On this contour, on beta, z equals, well, I can parameterize it by r, the distance from the origin. So it's going to be r times e to the minus I pi over 4, and that's a constant. So we know that dz is just this constant, minus I pi over 4 times dr. And we know that r is going to go from 0 to r times root 2. That's the length of this contour. It's root 2 times longer than one of the legs of this right triangle. Okay. Well, when we make this change of variables, things turn out nice and simple. We'll take this constant factor and just set it up front. Minus 9 pi over 4. And we have this integral from 0 to r root 2. Okay, and it's e to the minus I times this quantity here squared. Now when I square this exponential, I'm just going to double the angle. So I get e to the minus I pi over 2. Well, that's this angle down here, and the unit length complex number down here is minus I. So I'm going to get another factor, minus I times r squared, dr. And this minus I squared, well, that's just minus 1. So when I take the limit as big R goes to infinity, I get this expression that I wrote originally here, which we know how to evaluate. This is e to the minus pi over 4, minus I pi over 4, times, well, this should be, so maybe I should draw an arrow, as this is as r goes to infinity. This goes to root pi over 2. So we can actually evaluate that, and if we wanted, we could write this in Cartesian coordinates instead of this polar form, but it doesn't matter. So we know how to evaluate this green integral, and we're going to now show that this blue integral vanishes as r goes to infinity, and that will allow us to write this here. So now let's see what's going on. So first of all, from knowing that this function looks like a Gaussian as we proceed along this trajectory, makes it very much less surprising that the contribution to the integral from this region is small. After all, out here, this thing looks like e to the minus parameter squared. We call the parameter r, e to the minus r squared. So it's actually sort of quadratically exponentially damped out over here. Out here we only had 1 over r damping, but here we're going to have, I believe, e to the minus 2 r squared damping. So the contribution along here should be small in the sense of going to 0 as r goes to infinity altogether. And that is what we'll see. So we want to know the integral along, blue. The integral along this beta contour of e to the minus I c squared dc. And on this contour, on beta, z is, well, the real part's always I, and we can parameterize it by its actual imaginary part. Well, actually, this will be its negative imaginary part. So calling it y is maybe a little disingenuous, but nevertheless, the minus sign will be easiest, because this way, the parameter takes on positive values. Y is going to go from 0 to big R, and that's what we want. That turns out to be the easiest way to parameterize this. It's a little more inconvenient if you try to travel this contour up. So that's the case there, and we know that dz is minus I dy. Okay, so now it's not too hard to do the substitutions we need to do. We will be taking the integral from 0 to big R. That's the length of this contour, so that's not surprising. And now we have a minus I that we'll eventually need, and e to the minus I, r minus iy squared. Well, let's see, there will be a real contribution, r squared minus y squared, and an imaginary contribution, minus 2 ry I. Okay, dy. Not really room for that, but that's okay. All right, well, we only want to show that this goes to 0. So we really only want to know an upper bound on the absolute value of this. So in fact, I'm going to take absolute values of everything, and we'll see that this is not so bad. So in particular, this is no bigger than the result of integrating the absolute value of this integrand along this region. It's a like generalized triangle inequality. So this is no bigger than, well, I'll take amplitudes of everything in here, or absolute values of everything in here. This minus I is just going to go away. It's got absolute value 1. Then we don't care about the purely imaginary part of the exponent here, because e to the minus I r squared minus y squared, just this piece, is going to be of size 1. It's going to be on the unit circle as an exponential of something imaginary. But this minus I and this minus I are going to multiply to minus 1, and this will be no bigger than, so I want the absolute value inside the integral, from 0 to r, the absolute value, and now this is e to the minus 2ry dy. But this is an exponential of something purely real, so it's always going to be positive anyway. So in fact, the absolute value bars do nothing. And we can evaluate this integral, dropping the absolute value bars, pretty easily. When we integrate, we're going to get a 1 over minus 2r, and well, we can just see what happens. This is going to be, let me make sure I have this right. Yeah, e to the minus 2ry over minus 2r, evaluated. So you know what, I'll just erase this attempt at a dy here, and you know what I mean when I integrate this. Absolute value bars are still there though. This is evaluated at big R and 0. So you can see what happens. When we evaluate this at y equals big R, we get e to the minus 2r squared. That's going to go to 0 very quickly as r goes to infinity. And then in the denominator, we have this minus 2r. As r goes to infinity, that denominator is going to go to infinity, making this thing even closer to 0. And then the contribution at y equals 0 is just 1 over minus 2r, which also goes to 0. So you can see then, maybe I'll write it out more explicitly. We want to consider, so when I plug in r, I get, so r, I get e to the minus 2r squared minus 1. So it's easy to see everything here goes to 0 as r goes to infinity. In fact, if I just get rid of this, and this will be plus 1 over 2r, this clearly goes to 0, and this is a product of two things that go to 0 as r goes to infinity. So we really can make this as small as we like. And again, we have an exponentially suppressed contribution from this point down here, and a 1 over r suppressed contribution from this point here. So then we know, well, I'll even leave this up, but we know that the integral along beta ends up being negligible as r goes to infinity. So we can evaluate this integral by evaluating this sort of known integral, and in polar form at least it looks like this. Okay, and that's exact. That's it. That's how we did this integral. So, thank you.